So yesterday when we came across square roots of negative numbers, we said, hey, it's not real. It's still true, but now we're actually going to do stuff with it. Okay? So that's where the imaginary unit comes in. I cannot take the square root of negative 1 because there's no combination of negatives that I can, or of 1 that I can square that gives me a negative 1 radicand. So that's why we call it the imaginary unit. It is an imaginary number. So we use I to delineate the imaginary unit. Okay? So I equals the square root of negative 1. So whenever I have the square root of negative 1, I can just change it into I. And then now it's not in a radical anymore. Okay? So we treat it as its own special number. There's also a special property that when we have I squared, it equals negative 1. Because squaring undoes the radical. They're inverses. And so basically when we square the square root of negative 1, we have our radicand of negative 1. So we have these special principles and properties with the square root of negative 1. This idea extends to any negative number that is being square rooted. I can factor out that negative 1, square root it as I, and then continue to simplify the radical normally as I would in any other situation. So that way I'm not stuck on, oh, it's a non-real number. I can continue to simplify and use it and perform arithmetic with those values. Okay? So that's what we're going to do. We're going to start with the square root of negative 25. Always, always, always start by factoring out the negative 1. Always start by factoring out the negative 1. And then we can simplify any other way after that, depending on whether we have a perfect square or not. It's going to change how that looks, but we're using the same ideas as yesterday. So when I have the square root of negative 1, I know the square root of negative 1 equals I. And then what's the square root of 25? 5. Now, convention always dictates the I is after the integer factor. We write the integer factor first, and then we write the I. That's part of what we call standard form. There's a couple other nuances for standard form, and we'll go over those as we arrive with them. But we always have the integer coefficient and then I. I is always after it. Okay? All right? Negative 81. What am I going to split it into? Negative 1 and 81. Always start with negative 1. Make sure you get that out. It's so important. You factor out that negative 1 first before you do anything else. Okay? Is 81 a perfect square? Yes. Good. So I don't need to break it up any further. So square root of negative 1. I. And the square root of 81. 9. So I have negative I times 9. Negative 9I. We're preserving that negative that was outside of the radical when we started, so that's just following along as we go through it. Okay? Break apart square root of negative 7.
Negative 1 times 7.
Good. Okay? Can I simplify the square root of 7? No, so it's just going to stay in there. Alright? But I can still get rid of the negative 1 in the radical by writing it as the imaginary unit times the square root of 7. This is our other convention that we have when writing imaginary numbers. If you still have a radical, the I needs to be in front. So it needs to be after the integer factor, but it needs to be before the radical factor. Alright? So if we have all three, it's going to be sandwiched between the two. Alright? We'll see that on D. Alright? So I need to break this apart into negative 1 and 44. Does 44 have a factor that is a perfect square? 11 and 4. So I got 4 and I got 11. You're welcome. All right. So I got I got 4, I got square root 11, and I want the, nope, that's a 2. I'll be okay. Ignore that mistake. That's a 2. There we go. I want the integer coefficient first, then the imaginary unit, and then the radical. Both. Okay? Making sure it's in that order. The reason we have it in that order is for ease and consistency of readability. You guys having fun yet? I'm having fun. All right. So again, this just talks about the convention. You see how similar it is if we try to put the I after the radical. It's really easy to confuse whether or not it's outside the radical or inside the radical, which is why we have the convention of that. Now, we can multiply, we can divide, we can add, we can subtract, we can do all of that fun stuff with our imaginary numbers. So that's what we're going to do. All right? What's really important, though, is that we make sure that before we do anything else, we take that -1 out of those factors. You need to start with that, because if you don't, it's really easy to accidentally make it go away. If it goes away, you're going to get the wrong answer. Specific sum, okay? How many times have you put an answer in math lab and it was wrong because it was supposed to be positive and it was positive? Happens all the time, right? Those negative signs will get you every time. So this is super important that you do this step first, because it's possible, it's frequent, that that imaginary part is going to kind of go away and resolve. But there's a side effect of that imaginary unit disappearing, okay? So we need to make sure we start with this so that we have I square root of 6 times I square root of 5. We need to make sure we pull out that imaginary unit first. Okay? Now, I can go ahead and multiply these all together. I have I times I, which is going to be I.
I to the second power.
Good. Okay? Multiply those. I have my product rule and the square root of 30. We talked earlier, I squared equals -1. So I end up with negative square root of 30. Okay? Now, let me show you what happens if you forget to take out your imaginary unit first. Okay? And you go straight to multiplying these together. This is a no-no. Don't do this. Non-example. If you forget to take out the imaginary unit, you could just go ahead and say, all right, well, I'm going to take -6 times -5, which equals the square root of 30. Because -6 times -5 is a positive 30. Note the difference.
Can you do the last part again? The part from I to the second power.
I squared equals -1. -1.
Why? -1.
Square root of -1 squared.
But that's I.
I is the square root of -1. So if I have I times I, that means I have the square root of -1 squared. The square cancels out the radical, leaving me with -1. Okay? All right, so if you don't take out the imaginary unit, it's really easy to end up with the wrong sign, as we see that. Okay? This negative is an artifact left over from the fact that we had two imaginary numbers being multiplied together. Okay? So we need to make sure that we have that, so don't do this. All right? Let's look at B. We need to break apart the square root of -8. Okay? -1, 4, and 2. Square root of 6. -1. Let's go ahead and break this one apart too, as well. I don't have any perfect squares yet, but you're going to see why I do it in just a second if you don't already. Bring out the imaginary unit. So I've got I, and then I got 2. I can take out that square root, right? And that leaves me with 2. So I brought out both of those. I'm going to do the same thing over here. Times I root 3 times 2. If I bring these radicals together using my product rule, I have the square root of 2 times 3 times 2. If I multiply 2 times 2, what do I get? 4. What's the square root of 4? So I have another perfect square that I can bring out after I combine the two, because they had a common factor. So if I multiply these together, I get 12, and I could ask myself, okay, if 12 has a factor, that's a perfect square, 4. And so I could continue to bring out additional factors. So the combination of these two radicals gives me this. I'm going to go ahead and bring my other factors that I already brought out down. I've got 2i. Let me write it. I don't want to exit. There we go. I've got 2i times I gives me 2i squared. We'll deal with the 2i squared in a minute. And then I've got this pair of 2's, which gives me 4. I can square root that and end up with another factor of 2. And I'm just going to clean this whole thing up.
But can you just, so do you have to break that up, or can you just put it in as 6 multiplied by 12?
If you want, you can also take this and go, make sure you take out the -1. You got to do that. Okay, so you're going to have your I squared, because you're going to take those out, and you can multiply the 6 and the 8 with 6 times 8. 48, thank you. Okay. Then you could break 48 apart into its factors. That's fine. Either way, how you get down can vary a little bit, just depending on how you see the factors, where you simplify it. You may not know right off the top that these are going to have a common factor. Okay, so you may have to reevaluate. So the important thing is twofold. One, take out your -1 first. Okay, has to be done first. And then, as you start taking out other roots and combining using your product rule, just make sure that you keep in mind your final radicand cannot have any perfect square factors. So if you find that it does, after you multiply things together, then you need to make sure that you pull it out again. You need to keep pulling those out until we end up with our final answer. 2 times 2 gives me 4. I squared gives me -1. And then the 3. If you went with 48, what's the factor of 48 that's a perfect square? Here's a hint. It's square roots to give you 4. 16. So I could break this apart as times 3. I still have my I squared because I pulled out those negatives. Then I square root. Either way is fine. Whatever you want to do, you're still going to end up with, actually make that negative. You're actually still going to end up with the same number. So there's not one right way to factor it all together. You just need to make sure that you factor it all. You find all perfect square factors so that you can root those. You pull out the -1 first so you don't lose that imaginary artifact. Okay? So we end up with -4 root 3. Yeah. What 2? I still have I had, this was from the first one, 2i root 2. That's the first one. The second one was I times 3 root 3 times 2. That's there. That was the first one. This is all -8. This is square root of -8. This is square root of -6. I hadn't combined them yet. All right, C. What do I need to do first? So, factor out the -1 times 7. So I'm multiplying those all together. I just need to make sure I pull out that -1 so it doesn't go away. I need to preserve it. Square root of -1 is what? I. 5 times 7 is 35. No perfect square factors because those are the only 2 factors that are 1 in itself. So that's all there is to it. And it's not going to be negative because I only had 1 imaginary number, not 2. All right. Division. Same idea. Factor and simplify the radicals as much as you can. First things first, what am I going to take out? -1. All right. And then 80 has what factors? Which is the biggest one that's a perfect square? 8, 16, and... Nope. 5. Okay. So there's my numerator factored. I've got 2 perfect squares, and I like to square root of 5. Denominator, we're just going to have -1 and 5. So, square root of -1 gives me I. Square root of 16 gives me 4. Square root of 5 stays in. Square root of -1 gives me I. 5 stays in.
So when you find the square root of the number inside of the thing.
All right, walk me through B. -1. What else? 4 and 10. Okay, I can do 2 and 5, but I want you to notice. Just keep the 10, because we've already got that there. We know it's going to stay in. So there's no point in changing the denominator, because we can see into the future and say, oh, I'm going to be canceling that out. 10. Okay. Good. We bring out the I. We bring out the 2. We leave root 10 and root 10. Those cancel.
So I got it right. Yes, I did it on my head. Good job. Good job.
All right. Questions, comments, concerns? All right. Now.
Wait, no, can you go back to our copy now, please?
All right. So far we've dealt with imaginary numbers. Okay? They're just not real. When we combine imaginary numbers with real numbers, we get what we call complex numbers. Part of it's real, part of it's not. It's a complex personality. Okay? So, we have what we call the standard form of a complex number, where A is the real part and BI is the non-real part. Okay? Now, depending on some variations, we'll have some different terminology for it. So, we've got a complex number, A plus BI. If B is 0, that means that the second term is going to be 0. 0 times I is just 0. So the imaginary part doesn't exist. So we have a real number, just a pure real number. If B is 0, we have a pure real number. If A is 0, that means I don't have the first part. I don't have the real part. I only have the imaginary part. So that's considered a pure imaginary number. That's everything that we've dealt with so far. All right? Everything we've done today so far has been pure imaginary. If we have 2 parts together, if I hear you ladies talk over me one more time, I'm writing hours. Stop it. If I have both parts, then I have a non-real complex number. Now, once we have these complex numbers, what we can do is we can perform our normal arithmetic with them. Think of it as akin to combining like terms. I can only add a real number to a real number. I can only add an imaginary number to another imaginary number. So when we're adding complex numbers, we just need to compare and perform the operations on the real parts together and on the imaginary parts together. All right, so think of it like combining like terms with our algebraic expression. I can take -1 and I can add 9 to give me what? 8. And then I can take my imaginary parts. I can take -8i and I can subtract 3i to give me -11i. Not I squared, it's I. It's like combining like terms. I have -8 of the imaginary unit. I have -3 of the imaginary unit. Together I have -11 of the imaginary unit. So it's combining like terms. So let's look at our second expression. I've got 3 complex numbers being added together. My real parts are what? What are my real numbers? -3 plus 1 and -7. Okay? Those are the real parts. The imaginary parts. 2i minus 3i minus 5i. Okay? 2i is positive, so we're adding it together. So we just combine our like terms. -3 plus 1 minus 7. -3 plus 1 is -2. -2 plus -7 is -9. 2i minus 3i minus 5i. Positive 2 minus 3. Okay? And there it is.
The question.
Yeah.
Why did you do, first of all, why did you do 8i plus?
As opposed to what?
I don't know, this one you did, what's it called? You did 1 plus -7, so I think you did 8i.
Okay. Plus and negative is the same as subtraction. Write it in whatever notation you want. You can write minus 3i or plus -3i. Okay? And again, this is standard form. Has to be in standard form. Real part first, imaginary part second. Subtraction, same thing, but I have to have an extra step with subtraction. What's that extra step when I'm subtracting a binomial? So, I get -1 plus 2i minus 4 minus i. Add my real parts. What do I get? Good. Add the non-real parts. What do I get? I. Make sure it's in standard form. Distribute your negative. Add your real parts. What do you get? 8 and -12. -4. Add the imaginary parts. -2i. Okay? Distribute. -10 plus 6i plus 10 minus 10i. My real parts combine to what? 0. And my non-real parts combine to what? -4i. Okay? So C is pure imaginary. There's no real part. The rest of these are complex, non-real numbers. Okay? Complex, non-real, pure imaginary. Alright? So, adding and subtracting is akin to combining like terms. When I'm multiplying, I don't care about like terms. I just multiply. You just distribute. Okay? Just keep in mind that if you're multiplying a complex number by a complex number, then you're going to be having some exponents for your i's. So 6i times 4. What do we think that's going to be? 24i. So now a complex or imaginary number times a real number is going to give me an imaginary number. 6i times 3i. 18i squared. Now, what does I squared equal? -1. So that turns into -18. -18 times -1. Now, that's not in standard form. Good. -18 plus 24i. Okay? B. Walk me through it. 12, multiply. Keep going.
Plus 24i minus 6i minus 16i.
Which will turn into a positive 16. Combine like terms.
28
Standard form?
Yes.
And we're good. So we see how multiplying two complex numbers can give us real numbers. when we're done. I'm going to skip the next 3 slides. They talk about conjugates and division. I may come back to those, but we're not going to see a whole lot of it for a while. So we'll skip that. Okay. Last thing I want to talk about is finding powers of I. Okay. So we talked about square root of -1. Square root of -1 is I. I squared equals -1. Using that relationship, we can figure out if I have I raised to any power, I can quickly figure out what it's going to equal. So pay close attention to this pattern. Okay? So I to the 3rd power is, break it apart to I times I squared. All right? Those are the 2 factors. I is what it is. I squared is -1. So if I take I and multiply it by -1, I get -I. I to the 4th power, I use I squared for both my factors, which gives me -1 and -1, which results in a +1. Now notice when I go to I to the 5th power, I times I to the 4th. I to the 4th is 1. 1 times I gives me I. So now I'm back at I, which is saying the square root of -1. I to the 1st. I to the 1st. I to the 6th is 2 and 4. So I'm combining I squared and I to the 4th, which is -1 times 1 to give me -1. And the pattern repeats. It goes over and over and over and over. So it breaks down to I equals I squared equals -1, I to the 3rd equals I to the 4th equals, if I could write that correctly, the 4th equals +1. That's the pattern that repeats. Okay? Now there's a shortcut for finding which one it falls under. Okay? For any power of I. Alright? Babs, give me a number less than 100. 97. Okay? Take your exponent. Say I have I to the 97th power. Take your exponent, divide it by 4. I don't care about the quotient. What I care about is the remainder. Okay? So, how many times does 4 go into 9? 2. Okay? 2 times 4 gives me 8. Subtract, get a 1, bring down to 7. How many times does 4 go into 17? 4 times. Okay? 4 times that, 16, subtract. So my remainder is 1, right? Since my remainder is 1, I to the 97th power is equal to I to the 1st power. So if you have a remainder of 1, a remainder of 2, a remainder of 3, and no remainder. Because if there's no remainder, that means it goes in 4 times. Okay, it goes in evenly. That's going to be our 4th power. All right? So let's do that again. I to 28th power. Okay? I want to figure out it's going to be equal to I either to the 1st, 2nd, 3rd, or 4th. So 28 divided by 4. How many times does it go in? 7. Is there any remainder? No. No remainder. So, no remainder is I to the 4th. Okay? And this is why. Mathematically, this is what this breaks down to. Okay? Power rule of exponents. I can take I to the 4th and raise it to the 7th power, and I get I to the 28th. I to the 4th equals 1. 1 to the 7th power is still 1. So I'm repeating that pattern of I to the 4th, times I to the 4th, times I to the 4th, times I to the 4th, over and over and over. So when I have no remainder, if it goes in evenly, then I end up with I to the 4th, which is 1. Let's do it with 19. 19 divided by 4. So it goes in 4 times, giving me 16. So I have a remainder of 3. So I to the 19th is I to the 3rd. I to the 3rd equals what? Negative I. Make sense? Okay. Now, I have to deal with that -9. Do you remember what I do when I have a negative exponent? 1 over I to the 9th. So 1 over I to the 9th. But I'm going to do the same thing. If I divide 9 by 4, what's my remainder? 1. So it's I, 1 over I.
Question.
Then you didn't divide right. You should get a remainder of 6. Because if you get a remainder that's bigger than your divisor, then it means that you didn't put it in enough times. So you will only, as long as you do the division correctly, you'll only get a remainder of 1, 2, 3, or none. And that'll give you those powers of I so you can simplify it. Alright? Any other questions, comments, or concerns?